of all, what is a colligative property? A colligative property, this is an important definition, so circle this or something. A colligative property is a property of a solution that depends on how many particles are dissolved and not what the particles are. Now, this is crazy. So what this is saying is a solution that has the same number of particles as sodium chloride, as potassium bromide, they're going to have the same vapor pressure, freezing point, boiling point, and osmotic pressure. There are 4 colligative properties. There are 4 properties of solution that depend on how many things are dissolved and not what the things are. Okay, that's pretty crazy. That's what a colligative property is. Now, how do you determine the number of particles? Well, if you have an ionic compound, this can be a little tricky because ionic compounds dissolve and break apart into ions. I'll hop on the board here and talk about it before we get you a slide on Van Hoff correction factor. So if I have a polar solvent and I am dissolving an ionic solute, so a salt, right, which is an ionic compound, metal, non-metal. When a salt dissolves, it breaks up into its ions, and you have to count how many ions you get. For example, sodium chloride. When sodium chloride dissolves, it breaks up into sodium cations and chloride anions. So 1 molecule of sodium chloride generates 2 ions, 2 particles. And we have a term for this. It's called the Van Hoff correction factor. It's on the slide, chill. And we abbreviate it with a lowercase letter I. Okay, it's called the Van Hoff correction factor. And this would generate 2 particles. So this would have a Van Hoff correction factor of 2. 1 equivalent of sodium chloride generates 2 particles. So my correction factor is a correction factor of 2. Look at another one. What if I had calcium chloride? Well, now, when calcium chloride dissolves, it breaks up into calcium and 2 chlorides. So I get a cation and 2 anions. That has a Van Hoff correction factor of 3, right? So that would produce 3 ions. Let me give you some, and you try to determine the Van Hoff correction factor. Trying to determine the Van Hoff correction factor. I found the best way to do it is to write the balanced dissociation equation like I did above. Okay, write the balanced dissociation equation for these salts, and then count up the number of ions. Give those 3 a shot. All right, potassium oxide breaks apart into 2 potassium cations and an oxide. So that's 2 cations, 1 anion. That's a Van Hoff correction factor of 3. Sodium phosphate is going to dissolve into 3 sodium cations and a polyatomic phosphate anion. That's going to be 3 cations, 1 anion. That's a Van Hoff correction factor of 4. And then aluminum sulfate, that's going to break up into 2 aluminum cations and 3 sulfate polyatomic anions. That's a Van Hoff correction factor of 5. So hopefully you're getting that, right? We're going to have to work that into our formulas. If we have an ionic solute, then when we use our formula for change in vapor pressure, freezing point depression, boiling point elevation, and osmotic pressure, we need to factor in the Van Hoff correction factor to it because, colligative properties are all about the number of particles. Now, if you have a nonpolar solvent, then the only thing that can dissolve in you is a nonpolar solute. And nonpolar things are not ionic. They can't break apart into ions. So if you see nonpolar solvent, you don't have to worry about a Van Hoff correction factor. But if your solute is ionic, you got to worry about a Van Hoff correction factor. So how do you spell Van Hoff and all that jazz? It's on this slide. So Van Hoff correction factor, abbreviated with cursive I. And we actually already did this guy. This guy was a Van Hoff correction factor of 4. Right, and that was one of the ones that we did on the board. It says here, what is the Van Hoff correction factor for a non-electrolyte like a sugar or alcohol? A sugar or alcohol dissolves without breaking up into ions, right? It's not ionic. That is not an ionic compound. And if you have a non-ionic compound, if you have a covalent or molecular compound, then the Van Hoff correction factor is 1 because the whole molecule goes in, it does not break apart. Van Hoff correction factor be 1. All right. We're doing so awesome. And now to our first colligative property, which has to do with vapor pressure. So we should, and this is going to be Raoult's law. We'll get there. What is vapor pressure? Let's start with that. Vapor pressure is kind of like how volatile something is and how quickly it evaporates. Now, of course, because this is chemistry, we got to have a slightly more complex definition. Technically, in order to measure vapor pressure, it's got to be a closed system, and you have to wait and allow for an equilibrium to be established between evaporation and condensation. So essentially what you have to do is you can't put the lid on and measure the vapor pressure right away. You got to put the lid on. You got to give it some time to make as much gas as it's going to make, and then allow an equilibrium to be established between evaporating and condensing. And then that's when you measure this vapor pressure. Okay, that's all. Essentially, it's how volatile something is, how fast is it evaporating, but technically a slightly more complicated definition, right? All right. I would like you to not use this formula. I have found students do not have a lot of great success. Students tend to have way better success with this formula right here. So that's what I would write down. And this is going to be called Raoult's law, R-A-O-U-L-T apostrophe S, Raoult's law. And Raoult's law describes the change in vapor pressure for a solution. And it says that here's that mole fraction thing, right? Which is why we just spent the first part of class going over different ways to do concentrations. It says the mole fraction of a solute times the vapor pressure of the pure vapor pressure of the solvent all by itself, times the Van Hoff correction factor. That's how you're going to get the change in vapor pressure for a solution. So if you take the concentration of the solution in terms of mole fraction, and you multiply by the normal vapor pressure of the solvent before you dissolved anything, and then you multiply by the number of particles in there, the Van Hoff correction factor, then you can figure out the change in vapor pressure. And what my friend Raoult said is that the vapor pressure of a solution is always going to be less than the vapor pressure of the pure solvent. So what does that mean? That means essentially this. When I dissolve crap in my solvent, it's going to evaporate less. Notice this arrow is smaller and it's going to condense more. So the vapor pressure is going to decrease. The act of dissolving a solute in a solvent decreases the evaporation rate of that solvent. Okay, that's Raoult's law. It decreases the evaporation rate. And we can calculate it using this beautiful formula right here. So the change in vapor pressure is equal to the mole fraction times the pure vapor pressure of the solvent times the Van Hoff correction factor. Now, this next problem we want to do here, a little tricky, because I'm going to give you the concentration in mass percent, and we're going to have to convert it, okay, to mole fraction. So that's going to be a concentration conversion to do first, and then we'll use this formula. So here we go. Let me pop this slide up here. Let me copy some stuff down, and then we'll do it. So why don't you read that problem? How much lower is the vapor pressure? While I write the important information up here. Awesome. All right. So the formula we'd like to use eventually is the change in vapor pressure formula, because I want to know how much lower is the vapor pressure. So what's the change in the vapor pressure? And the change in vapor pressure is going to be equal to the mole fraction of the solute, which is sodium chloride, times the pure vapor pressure of the solvent, water, times the Van Hoff correction factor. And we really have two of these things to start with pretty easily. We have the pure vapor pressure of the solvent. That's that. So this is going to be 23.78 torr. And you guys should be able to give me that Van Hoff correction factor. Why don't you think about the Van Hoff correction factor there for a second? What's going to be the Van Hoff correction factor of sodium chloride? Think about that. Hopefully you're saying it's 2, right? Because when sodium chloride dissociates, you get one sodium cation and one chloride anion. Van correction factor 2. So all we need is the mole fraction. Here's the problem. We were given the wrong concentration unit. We were given the concentration in percent mass. That's not good. So this is called what I like to call a concentration conversion. One of your homeworks is on trying to do this. Some of these are really tough. Some of these are not too bad. This one's in the middle. Okay, so we're trying to go from percent mass to mole fraction. Now, the first thing that I recommend when you get this is to write the formula for both. So percent mass is going to be the mass of the solute divided by the total mass of the solution times 100. And then mole fraction is going to be the moles of sodium chloride divided by the total moles of the solution. So what do we need to do here? Well, what I like to do is when I'm trying to go from percent mass to something, well, a lot of times it's beneficial to assume 100 grams. Because if I assume 100 grams, if this is 5.50% sodium chloride, then that would be 5.50 grams of sodium chloride. And then the rest must be from the solvent, which is 94.50 grams of water. Do you see? Assuming 100 grams, when you get stuck a lot of times, see if you can't assume 100 grams and see if that helps. By assuming 100 grams, I got 5.50 grams. If it's 5.50% by mass of the solute, then that would be 5.50 grams of the solute. And then the rest would be from the solvent. That's where the 94.50 grams of the solvent comes from there. So now here's the nice thing. Now I have numbers. And now what can I do? Well, I could take this mass of sodium chloride and turn that into moles of sodium chloride. And then I could take this mass of the solvent and turn that into moles of solvent. And then remember that a solution is the moles of the solute and the moles of the solvent. So here's what I need you to do. I need you to do some simple stoic for me here. I'm going to give you a minute or two. Okay? I need you to convert 5.50 grams of sodium chloride into moles of sodium chloride. Then you need to convert the 94.50 grams of water into moles of water, and then plug that stuff in, turn it into a mole fraction. And then we'll have our mole fraction, we can get our change in vapor pressure. So go ahead and give that a shot. Okay, so convert simple stoic here, one-step stoic, masses to moles. You got this. Dropping like flies on Zoom tonight. All right. Mole fraction is a unitless concentration, by the way. If you think about it, it's going to be moles divided by moles. So the moles cancels out. All right, so we got a mole fraction here of 0.0176. So how are we going to get the change in vapor pressure? 0.0176. Again, no unit. Mole plus mole is mole. Mole divided by mole cancels out. So 0.0176 times 23.78 torr times 2. It doesn't matter what unit your pressure is in. Whatever unit your pressure is in, that's going to be the unit of your answer. So the change in vapor pressure is going to be 0.0176 times 23.78 times 2. And that's going to be a 0.837, looking like 3 sig figs. I would take 4 here, 0.837 torr. And that answers the question that we were asked. So the question we were asked is how much lower would the vapor pressure be? Well, the vapor pressure would be 0.837 torr lower. Okay, it'd be lower. Now, if the question had asked, what would be the new vapor pressure? So you got to be really careful. But what if the question said, so we got 0.837. What if the question had said, what is the actual vapor pressure? What's the new vapor pressure of this solution? Well, now you need to know Raoult's law. Now you need to know that when you dissolve something, the vapor pressure always goes down. So here's how we could calculate that. The normal vapor pressure is 23.78 torr. That's what the vapor pressure is normally. It's now going to be 0.837 torr lower. So the new vapor pressure is going to be the original 23.78 torr minus the change 0.837 torr. We'll do addition, subtraction, sig fig rules, and we'll stop at the hundredths place. The new vapor pressure is going to be 23.78 minus 0.837. That's going to be 22.94 torr. That'd be the new vapor pressure. Now, I stole this image here, and I love it because this scientific illustrator absolutely knew what they were talking about. If you look at this image, here is the vapor pressure of pure water. You can see the gas this is a YouTube manometer. You can see the gas is pushing here, air is pushing here. So this would be my vapor pressure. That's how much the solution is pushing back. When we dissolve some solute, look what happens. It's not pushing as hard. Air is winning. Atmospheric pressure is if this is a push of war, the act of dissolving something in here now causes less of the particles to be in the gas phase. It can't push back as much. So yeah, now we get that. Love that. And again, our final answer should be exactly what we got there, 22.94. So this is Raoult's law. This is change in vapor pressure. How much is the vapor pressure going to change by? The change in vapor pressure is equal to the mole fraction times the pure vapor pressure of the solvent before you dissolved anything times the Van Hoff correction factor. That's how you're going to find that. Beautiful formula. That's our first colligative property, and now it's time for our second one. And you actually already know our second colligative property. You just don't know that you know that you know it. Our second colligative property says this: it's freezing point depression. When you dissolve a solute in a solvent, its freezing point drops. And you know this because, well, it used to snow around here. Okay, I'm a big winter guy. I'm an avid snowboarder. I love snow. Like I just, oh my goodness, love the snow. It just doesn't snow anymore. It's just crazy, but it used to snow around here. And back when it used to snow and get icy, we used to put salt on the roads or the sidewalks. Why did we do that? Because adding salt to water lowers its freezing point. So the water doesn't freeze at 0 anymore, or 32 degrees Fahrenheit, okay, 0 degrees Celsius. It'll now freeze below 0 degrees Celsius or 32 degrees Fahrenheit. And if it's not cold enough out, then the ice will melt. So that's why we add salt. Salt is a solute with a Van Hoff correction factor of 2. And by adding a solute to a pure solvent, you can lower that solvent's freezing point. And here is the formula. This is what you're going to want to write down, ladies and gentlemen. The change in temperature of freezing, how much the freezing point will change, is equal to the molality, not molarity, but molality, times a constant called the freezing point depression constant times the Van Hoff correction factor. Notice we are using molality here as our unit for concentration. Why is that? Because temperature is changing. And when temperature changes, you cannot use molarity. Molality, okay, has kilograms of solvent in the denominator instead of volume. And mass is not going to change with temperature, but volume will. as objects expand and contract. So we have to use molality here. We have to. Okay, remember molality is moles of solute per kilogram of solvent. And then we need a freezing point depression constant. I'm going to tell you this right now. For the homeworks, you will have to come back to this table right here in the slides, or Google it, or look it up in the book. But I think there's a homework problem where I don't give you the freezing point depression constant. You need to go find it. Go find it here. Okay, so what we've got is we've got various solvents, and we have the freezing point depression constants for them. We also have the boiling point elevation constants, which is going to be coming next. So for example, the freezing point depression constant of water is 1.86 degrees Celsius per mole. So weird units on these constants, degrees Celsius per mole. So let's try this out. So here we have a really weak antifreeze solution. So you probably know that, hopefully you know, I don't know, with new cars and kids these days, I don't think anybody knows anything. Okay, but your radiator in your car is the coolant system for the car, and it circulates, okay, coolant, a fluid, through your engine to cool it down, or your engine would just get way too hot. It would just melt, right? You know, obviously electric car is different, totally different animal. Anyway, you could get by in the north here, putting water in your radiator and driving around, and you would be fine until the temperature dropped below freezing, and then your car not going to be so fine because your radiator, the water in there would freeze and then expand, and your radiator would crack, and now you got a couple $1,000 car bill, and it's not going to be fun. Okay, so what do? Well, they dissolve a solute in the water called ethylene glycol. It is a non-electrolyte. It's an alcohol. It's a diol. Okay, every once in a while, it's got a really sweet taste, but it's a poison. Don't taste it. Every once in a while, you get to hear some stories. Some wife poisoned her husband by putting ethylene glycol, antifreeze, and some Jello, and then they ate it and died. You know, whatever. Don't do that. Don't do it. Don't do it. But you know that still happens. I mean, you're gonna get caught. They're going to do an autopsy. You're going to get caught. I don't get it. Anyway, I want to calculate how much an ethylene glycol solution depresses the freezing point. Now, in your car radiator, it's about a 50-50 mix here in Pennsylvania, and in a lot of parts of the Northeast, you know, even, you know, Vermont, you know, whatever, that 50-50 ratio of ethylene glycol and water is going to be fine. Now, if you were driving to the Arctic Circle or something, you're going to need it to be actually a little more concentrated. You need a special antifreeze because it gets so cold up there, and in parts of like Siberia and northern Russia, it gets so cold, a 50-50 mix is not going to cut it. Like, that's how cold it gets there. It would still freeze. But anyway, I want to do a far less concentrated solution than that, right? So an ethylene glycol solution, super concentrated. In your radiator, 50-50 mix, super concentrated. But I want to do this 1.5 mole ethylene glycol solution. I want to calculate the freezing point depression for that. And here's the freezing point depression cost for water, which I just ripped off of that last slide, 1.86 degrees C per mole. Give me a second to copy this stuff down. We'll do this problem together. All right, first thing I would do is write the formula for freezing point depression. So the formula for freezing point depression is the change in temperature of freezing is equal to the molality times the freezing point depression constant times the Van Hoff correction factor. This is going to be an easy one. We have the molality. We have the freezing point depression constant. We just need the Van Hoff correction factor. And here's the good news. Ethylene glycol is not an ionic compound. It is not a salt. It does not break up into ions. So the Van Hoff correction factor for a non-electrolyte, a non-ionic compound, is going to be 1. So we're ready to rock here. The change in temperature of freezing is going to be the molality, 1.5 mole, times the freezing point depression constant, 1.86 degrees C per mole, times the Van Hoff correction factor, which is 1. Now, when we do this, the molality cancels out, and we're left with degrees Celsius. This is good news, people. We're looking for a change in temp. You can measure temp in degrees Celsius, so that's good news. So 1.5 times 1.86, that's going to be a 2.8 degrees Celsius temp change. So what does that mean? Well, the freezing point of water, when you dissolve enough ethylene glycol in it to make it a 1.5 mole solution, the freezing point is going to be depressed by 2.8 degrees Celsius. So what's the new freezing point? Well, water normally freezes at 0. it's depressed by 2.8. So the new freezing point is negative 2.8 degrees Celsius. That would be your new freezing point. You got to be careful what the problem's asking for. Does it want to know what the freezing point depression is? Well, it was depressed 2.8 degrees Celsius. Or does it want the new freezing point? The new freezing point, because water normally freezes at 0, if it's depressed 2.8, the new freezing point is negative 2.8 degrees Celsius. Not a hard formula. Sometimes, maybe maybe you'll have to calculate the molality and we'll just give it to you. Obviously, the ethylene glycol in your car's radiator is far more concentrated. That's still, it gets colder than that sometimes, not very often, right? But it gets colder than that around here. So you don't want any chance of your radiator freezing, right? So 50-50 mix is way more concentrated than that. Awesome. Just like freezing point depression, the opposite of that is boiling point elevation. When we dissolve a solute in a solvent, the boiling point actually goes up. So water normally boils at 100. If I dissolve something in the water, now it's going to boil higher than 100. Now, traditionally, for most solvents, the boiling point is not nearly as affected as the freezing point. The freezing point is almost always, except for a couple solvents like diethyl ether, the freezing point is almost always affected more than the boiling point. Almost always. So here's our formula. It's going to look almost identical to the last one. The change in temperature of boiling is equal to the molality times the boiling point elevation constant times the Van Hoff correction factor. The change in temperature of boiling is equal to the molality times the boiling point elevation constant times the Van Hoff correction factor. Okay, swap the F's for B's, and you got the boiling point elevation formula. So what would be the new boiling point of this 1.5 mole ethylene glycol solution? Now, the boiling point elevation constant, as I was saying, is almost always lower than the freezing point depression constant. So for example, before we do this problem, if I go back, come on now, PowerPoints. If we look here, look at the freezing point depression constants and look at the boiling point elevation constants. The freezing point depression constant is almost always larger than the boiling point constant. Now, the exception being diethyl ether, where the boiling point's actually affected a little more than the freezing point. But like, look at carbon tet, freezing point way more impacted than the boiling point. Chloroform, freezing point more impacted than the boiling point. Water, freezing point more impacted than the boiling point. Essentially, what I'm saying is most of the time, freezing point gets depressed more than the boiling point gets elevated, but they both do. It's essentially extending the range at which the substance is a liquid, right? Lowering the freezing point, elevating the boiling point, extends the range on both ends. Anyway, let's calculate the change in temperature of boiling here for this 1.5 molal ethylene glycol solution. Go ahead and give it a shot. So you should get 0.77 degrees Celsius as your change in temperature of boiling. So 1.5 molal times the boiling point elevation constant, 0.512, times the Van Hoff correction factor of 1. That's a 0.77 degrees Celsius change for boiling. What does that mean? The new boiling point for water normally boils at 100. The new boiling point is going to be 0.77 degrees Celsius higher. That's 100.77 degrees Celsius. A 1.5 molal solution of ethylene glycol in water is now going to boil at 100.77 instead of 100. Not a big difference. About 101, about a 1 degree Celsius difference here. So boiling point usually not nearly as impacted as freezing point. Now, I don't know if you got phase diagrams in Chem 101 or not. Here at Hack, we usually don't do phase diagrams till Chem 102. We're going to do this on Wednesday, in fact. But if you've gotten phase diagrams before, you could see essentially the blue line is like normal pure solvent, and you can see when it is a liquid. And the red line now would be for a solution where it's a liquid longer. So it freezes at lower temperatures now and boils at higher temperatures. So it extends the range that substance is a liquid. If you've never seen a phase diagram before, that'll make a lot more sense on Wednesday. Our last colligative property is osmotic pressure. Osmotic pressure is well, hopefully you've heard of osmosis before. Let's stop and talk about that. I tend to have like all bio majors, right, in my classes. Like everybody's a bio major. Where are the chem majors? That's what I want to know. Where are they? Doesn't this look like fun? Come on, guys. Hopefully you remember what osmosis is, at least from high school, even if you're not a bio major. So osmosis is the spontaneous movement of water across the semi-permeable membrane, like cell membrane, but you got that phospholipid bilayer, right? All this craziness, okay, the tails, and then, they all draw phospholipids like that and all that junk. Anyway, osmosis is when water moves into and out of a cell, depending on concentration. So for example, say that we take a cell and we put it in a high concentration of salt. So we dump that cell in a salt water solution. So there's way more salt outside than inside. Okay, the cell and the environment want to have the same concentration. Okay, but it takes energy to move salt in and out. They do have salt channels in cells. I'll let your bio professors teach you all that junk. Okay, but that takes energy. It takes that ATP stuff. But what gets to move for free is water. It's water, yeah. So what's going to happen here is osmosis would go in this direction. Water would leave the cell. It's going to leave the cell for two reasons. It wants to dilute the environment. And by moving solvent out, you're going to make the salt that's in here, you're going to make the cell more concentrated. Water always moves from a low concentration to a high concentration. Okay, so if I have some salt in here, but there's more outside, by shrinking the volume, this has now become more concentrated because water left. Now, eventually, though, if you put it in too hypertonic of an environment, okay, the cell will shrivel up and die. Can't move it. If it moves too much water out, it's gonna, it's gonna rip open and die, shrivel up and die. The opposite would be true, though. If I would take a cell, for example, and put it in distilled water, pure water with no salt, just water. Well, now it's more concentrated in the cell than out. So water would move in, and now the water would just keep moving in because it's never going to be able to dilute it enough, and the cell would explode, and you get lysis in that direction. So water, osmosis is always the movement of water from less concentrated to more concentrated, always less to more. And this happens spontaneously. Here's how we're going to describe osmotic pressure. I don't know if you've ever seen a dialysis tube, but this is essentially a dialysis tube where you have a semi-permeable membrane disc in the middle. This would be like a cell membrane. And we have a salt water solution on one side, pure water on the other. And when we allow these two to mix, the water is going to travel through here. So the salt can't come over, but they want to mix. So osmosis is going to happen, and water is going to go from less concentrated to more, and some water is going to move over here. Essentially, here's what osmotic pressure is. Osmotic pressure is how much pressure we would have to apply to this to prevent osmosis from happening. So imagine we had a piston on here or something. How much pressure do we need to apply to keep that water from coming over? How much pressure needs to be applied to prevent osmosis? That's how I like to think of osmotic pressure. And of course, we got a formula for this last colligative property, and it's a weird one. Our symbol for osmotic pressure is capital pi. So you're used to lowercase pi, 3.141, whatever in math class. This is capital pi. That's our abbreviation for osmotic pressure. And the osmotic pressure of a solution is equal to the molarity. So we can get away with molarity here because we're not changing temp. So we don't need molality. Molarity is fine. Osmotic pressure is equal to the molarity of the solution times the universal gas constant. That's right. You thought you were done with that in Chem 101. 0.08206 atmospheres times liters over moles times Kelvin times the temperature, which of course is going to have to be in Kelvin because of the constant, and then times the Van Hoff correction factor. So because we're using the universal gas constant R, and because it has units of atmospheres times liters over moles times Kelvin, this means their osmotic pressure is going to be in atmospheres, right? And our temperature has to be in Kelvin. So watch out for that when we're doing these osmotic pressure problems, okay? We are going to do a pretty darn hard one. There's a really easy one in the homework where you essentially plug the molarity, RT, and I in and solve for osmotic pressure. We're going to do a harder one here tonight. And the harder one here tonight is going to be analogous to what we're going to do in the lab tomorrow. So tomorrow's lab is you're going to try to get the molecular weight of substances, the molar mass of substances based on the freezing point depression. So we're going to do freezing point depression tomorrow in lab. But this is osmotic pressure. So we're going to try and get the molecular weight of something using osmotic pressure. This is a little more difficult. And usually, this is why I think my friend Greg is testing proteins. Usually, osmotic pressure, when you're trying to get molar masses, is for big substances, the things with a really high molecular weight. That's usually why you would do that. So that's why I'm thinking his group is probably testing some protein-based drug. Just a guess. I don't know. He never tells me. So let's take a look at this problem. I want to get the molar mass of a protein. Remember, proteins are macromolecules, right? Again, you guys are usually bio people. So I don't know. I'm going to learn about you tomorrow. Maybe I'm wrong. Maybe I got a whole group of chemists this time. Probably not. So I want to know, what is the molar mass of a protein when 8 milligrams of that protein is dissolved to make 15 milliliters of solution at 25 degrees Celsius, and the osmotic pressure of that solution is 3.65 torr. So essentially, you have to apply 3.65 torr of pressure to prevent osmosis from happening when the solution is created. Give me a second. This one will take some paper. Okay, so let me copy some of this information down on the board, and we're going to go through it. This one does take a little bit of time. All right. So I wrote down the pertinent information. End of the day, we want the molar mass of this macromolecule, this protein. We know we dissolved 8 milligrams of it, 15 mils of solution. We know we're at 25 degrees Celsius and we have the osmotic pressure. So the first thing we're going to do is I'm going to write that osmotic pressure formula. So the osmotic pressure is equal to the molarity times the universal gas constant times the temperature times the Van Hoff correction factor. Let's kind of check off what we have, what we don't have. We have the osmotic pressure. We know R is 0.08206 atmospheres times liters over moles times Kelvin. We know R. We know the temperature. We're going to have to turn it into Kelvin, but we know it. And we also know it's a protein. That's not an ionic compound. Proteins are macromolecules. So there's going to be a Van Hoff correction factor of 1. We know that. Only if this was an ionic compound, metal, non-metal, right? That's when you have a Van Hoff correction factor other than 1. So the issue people often have with this kind of problem is it's hard to see the whole thing. You have to kind of break it down into steps. What do I have? What do I not have? I have this, I have this, I have this, I have this. I must be solving for the molarity at first. And that's the key to the problem. The first thing you're going to do in this problem is, if I know the osmotic pressure and the rest of this crap, I can solve for the concentration of this solution. What am I going to do after that? We'll worry about that afterwards, right? We'll worry about that in a minute. That's 60 seconds from now problem. But right now, can we just get that molarity? Now, I like to do algebra up front. So if I want the molarity, I'm going to divide both sides by RTI. The molarity of the solution is equal to the osmotic pressure divided by RTI. So the osmotic pressure, we got a problem. R has units of atmospheres. We're given the osmotic pressure in torr. So we need to convert from torr, or millimeters of mercury, because the torr and a millimeter of mercury are the same thing. They named a millimeter of mercury after the guy that developed the barometer. His name was Torricelli. Okay, so anyway, there are 760 torr in an atmosphere. So we need to take 3.65 divided by 760. So 3.65 divided by 760, that is 0.00480 atmospheres. We can now plug that in for that, 0.00480 atmospheres. Then we got R, 0.08206 atmospheres times liters over moles times Kelvin. That's R. Now we need temperature. 25 degrees Celsius, we're going to add 273. That's 298 Kelvin. So that's what goes in for T, 298 Kelvin. And then I, the Van Hoff correction factor, is 1. Take a look at what's going to happen here. It's pretty awesome. Atmospheres cancels out. Kelvin cancels out. We're left with liters in the denominator, and moles is in the denominator of a denominator, which means it belongs in the numerator. So when we calculate this, we're going to end up with units of moles per liter, which is awesome because that's what molarity is. So we're going to punch this in. Okay, our pressure in atmosphere is 0.0048 divided by R, 0.08206 divided by T, 298. And we get 1.96 times 10 to the negative fourth molar. Not very concentrated. Think about it, you only put 8 milligrams in 15 mils. It's not very concentrated. So this is the concentration of our protein mixture. So this is the first step. Okay, getting molarity from osmotic pressure. And now we're going to kind of work it backwards, right? End of the day, molar mass, molecular weight, is the mass of a substance divided by the moles. Now I know the mass of the solute. I put 8 milligrams in there. So if I divide that by 1,000, because there's 1,000 milligrams in a gram, that's going to be 8 divided by 1,000. That's going to be 0.00800 grams. That's the mass. If I can figure out how many moles are in here, I know its mass. How many moles is it? If I can get its amount, that goes in the denominator. I can get the molar mass. So how do I get that amount? Here's how. Molarity is the moles of a substance divided by the volume. But that volume has got to be in liters. So if I multiply both sides by the volume, what we find is the molarity of a substance is equal to the... No, I'm so sorry. What we find is the moles of a substance is equal to the molarity times the volume in liters. This is how we're going to get the moles. We're going to take the concentration, 1.96 times 10 to the negative fourth molar, times the volume in liters. We have the volume in milliliters. There's 1,000 milliliters in a liter. That's 0.0150 liters. If you're super into units, remember capital M molarity is moles per liter. So the liters cancels out, and we are left with moles. So 1.96 e negative 4 times 0.015. That's going to be 2.94 times 10 to the negative 6 moles. That's the amount. Remember, molar mass. What are the units of the atomic masses on the periodic table? Grams per mole. You have the mass in grams. We just got the moles, 2.94 times 10 to the negative 6 moles. This substance, remember, it's protein. This substance has a molecular weight of 2,720 grams per mole. I rounded it to 3 sig figs. This is a heavy guy. It's a protein. It's a macromolecule. It's going to have a big molar mass. Tomorrow in lab, we'll do something similar. Tomorrow in lab, you'll use freezing point depression. So we're going to solve for we'll get the freezing point depression. You'll solve for the molality. Then we're going to, here we solve for the molarity. And we worked backwards to get the molar mass. Tomorrow, you're going to do something very similar. You're going to solve for the molality, and then you're going to work backwards. That is it